And we are recording. Okay, I wanted to start today with just one more problem of the kind of heat conduction that we did yesterday. And then we'll look at some where we start involving time and see how those work out. But here's the problem. This is one I made up. I've just been fantasizing about this. We were replacing the windows that were in our house in Moses Lake at one point, and they were actually dual pane windows. So this problem's a little bit fictitious, but you can buy single pane windows for pretty cheap nowadays, and you can use them for stuff like greenhouses and things like that. So, but for insulation in the walls, I wanted to use straw bales. That's one way of doing things, and a straw bale might actually be 18 inches thick, so or provide you with that much insulation. And you put it in between two walls where you'd have possibly some kind of maybe two stud walls, and then in between them would be this straw bale. And you could use fiberglass in those stud walls if you wanted to, or you could just not insulate them. But it's one way of doing it. And there's a building in Ellensburg. If you ever are ever over in Ellensburg, there's a Fred Meyer store there. And across the street from that is a coffee shop. I'm trying to remember the name. I can't remember the name of the coffee shop right now, but they have straw bale windows and they're about a foot thick. It's kind of interesting to see. Anyway, but that was the idea. And for the windows, I was going to use some old windows recycled from my previous house. And each window would consist of two single pane windows separated by a foot of dead air space. And for this problem, we're going to use our imaginations a little bit. If the outside air is at minus 15 degrees Celsius and the inside air is at 21 degrees Celsius, which is a comfortable room temperature. In fact, it'd be a little bit warm for a shop where you're doing physical labor much of the time. What's the heat loss through a 9-foot squared window? So we've got a bunch of unit conversion on here, and I think I made...
There's too many students for that.
Pardon? Whoops. What did you say, Alex? Or you just accidentally unmuted? Okay. Anyway, what's the heat loss through a 9-square-foot window? So I think the first thing I'll do is do some unit conversion to figure this out. For one thing, 1 foot, if it's a foot of dead air space, and let's just assume we have two significant figures on this. So 1 foot times 1 foot, let's see, it's 12 inches per foot times 0.0254 meters per inch. And by the way, 1 inch is exactly 2.54 centimeters. So I've got an infinite number of sig figs here. But if you do that, you end up with, for two significant figures, 1 foot is equal to 0.30 meters. So that's the amount of dead air space you're going to have in between these panes of glass. So 0.30 meters. And then let's see, I've got a 9.5 foot squared window. So 9.5 feet squared times 0.30 meters per 1 foot. And you square that. And I don't know how many we'll have, but and it helps to turn on your calculator. It'd be about 0.86 to two significant figures meters squared. So now we've got pretty good stuff here. The temperature hot minus temperature cold is TH in here and TC here. This is minus 15 degrees Celsius. This is 21 degrees Celsius. So there's my TH, there's my TC. And after this, I'll set it up like I did the ones yesterday, where thing that I'm gonna have to know. Man, that's the second time today my phone's rung. And I don't recognize the number. Still, I'll turn it off. Okay, things I'll need to know are the thermal conductivity of glass. And that happens to be something that I used yesterday and will use again today. Let's see, 0.96. And this is watts per meter Kelvin. And that of air is equal to 0.0262 watts per meter Kelvin. So those are all constants that I'll need for this thing. And now I can set up the problem that I'm going to have to solve. And I won't plug these numbers in for a little bit, but I will eventually. Oh, by the way, on this thing, I've got two more temperatures that I want to use. I'm going to have a T2, which is the temperature of the inside surface of this pane of glass. And then I will have a T3, which is the inside temperature of this pane of glass, the one that's closest to the outside. Now, let's see. Oh, one thing that this is a bit bogus as far as the problem goes. 1 foot of air doesn't actually give you that much dead air space because convection currents would transfer heat from one window to the other effectively. And the maximum effective airspace is only about 15 to 18 millimeters. Still, you'd have, say, 15 millimeters of dead airspace on this side, and you'd have another 15 to 18 millimeters of dead air on this side, which would be pretty effective, but we're going to pretend that we have the full 0.30 meters of dead airspace. And so that part won't quite be bogus, but anyway, we'll set up an expression for the heat flow through this pane of window, the heat flow through this air gap, and the heat flow through this pane of glass. And for exciting details on that, you can look at yesterday's video. But we'll have H is going to be the same for all three. And so for the first one, I will have its glass. So I'll have the thermal conductivity of the glass times the area of that window. And then I would have the temperature on this side of the glass minus the temperature on that side of the glass. So TH minus T2 divided by the thickness of the glass, which is given up here for 6 millimeters. Only one sig fig on that, so we'll probably just have one sig fig when we're done. I didn't set this problem up ideally. I should have given that two significant figures. Or we could pretend it's 6.0. Anyway, that's the first one. The second H equation that we'll get will be for this 1 foot air gap, or 0.30 meter foot air gap. This will be the warm side of it. This will be the cool side. So for that one, I'll have the thermal conductivity of air times the area of it. And then T2 minus T3 over the thickness of the air. And so that's our second equation. And then the third one, have the same H. It's going to be the glass again. Kg times A times T. This time the warm side is T3, the cold side is TC. So, and that's over the thickness of the glass again, and it's an identical piece of glass to the one that's up here. So I'll be able to take advantage of that to simplify a little bit of the algebra. Okay, and I'm doing this exactly like I set the problems up yesterday, because if you were given a problem like this on the test, you're not going to have the intermediate or some of the equations that we develop from this. You're going to have to develop those yourself. So keep that in mind. All right. Well, what I did yesterday was to solve for the temperature differences in each one of these three equations. And in each case, I'll multiply out from underneath by the thickness of the glass and divide by the conductivity times the area. And I'll get the first equation will be H times the thickness of the glass divided by the thermal conductivity of the glass and the area of the window. And that will equal just TH minus T2. Then I do it again for the second equation. For that one, I'll have H times the thickness of the air divided by, let's see. Going to need more room down here. Always lots of scratch paper in my house. And this will be thermal conductivity of the air times the area of the window. And that one will equal T2 minus T3. And then when I do the same thing for this third equation, and be careful in the algebra on here, by the way, this is an easy place to make a mistake. Multiply out from underneath by the thickness of the glass again. So I'd have H times the thickness of the glass divided by, let's see, K sub G times A. And that will equal T3 minus TC. And as we did yesterday, if you look down the right side of this equation, TH minus T2, T2 minus T3, T3 minus TC, I can add these three together and add these three together. And what'll happen on this right side, let's see, will this still show? Yeah, is that the T2s will divide out because I've got a minus and a plus. The T3s will not divide out, but add out because I've got a minus T3 and a plus T3, and I'll just end up with TH minus TC, both of which are numbers that I know. Now, this part's a little bit messier. I'm going to move up here to write that out. But I'll have the first and the third left sides are identical. So I'll have two of those. So I'll have 2 times H times the thickness of the glass divided by the K sub G times A, the thermal conductivity of the glass times the area, plus I'll have this one for the air. H times the thickness of the air gap divided by K sub air times A. And then that'll just equal the TH minus TC. Okay. I'm going to start by multiplying both sides by the area because that'll simplify things a little bit. And then on this side, I'll have 2H T sub G over K sub G plus H T sub air over K sub air. is going to equal that area times TH minus TC. And then I'll factor out the H's and divide by what's left inside there. And so I'll have H is going to equal the area times TH minus TC divided by 2T sub G over K sub G. Plus T sub air over K sub air. Okay, and now I can set up something that just has the numbers in it. And when I do that, let's see, the area of the window here, I figured out somewhere, was 0.86 meters squared. pH was 21 minus a negative, well, it's 21 degrees Celsius minus negative 15 degrees Celsius, and I'm going to do that in my head. That's 36 degrees Celsius, but it's also 36 Kelvin because a temperature difference is the same in Kelvin and Celsius. And down on the bottom, I'll have this 2 times the thickness of the glass, and let's just call it 6.0 so I can keep 2 sig figs on this. So 2 times 6.0 times 10 to the minus third meters divided by the thermal conductivity of the glass, which I looked up. It's 0.96 watts per meter Kelvin. And then I'll have plus the thickness of the air. Okay, really thick, 0.30 meters. Divided by K for the air, which is 0.0262 watts per meter Kelvin on that. Okay, and now that I've got that stuff kind of settled down, I'm going to do something that I did yesterday, and that is to calculate this one and calculate this one. I could wrap it all in parentheses, but I want to see how much more that the air provides insulation than the glass does. So I'll calculate the first one, which is going to be 12 times 10 to the minus third divided by that thing. And I get, now the first one is 1.25 times 10 to the minus 2. And the units, I've got units on the bottom in a fraction, flip it and multiply times that, and I'll have Kelvin meter squared per watt. And then I also add to that 0.30 divided by 0.0262. Which ends up being 11.5. Let's see, 2 sig figs, yeah. 11 Kelvin meters squared per watt. Okay. This is 1/8, 1.25 times 10 to the minus 2. And if I divide this by that, I would get 1.25 -2. I expect 88, but we'll see. Actually, I get 92 because this isn't exactly 11. But anyway, this is 92 times as great as that number. So the insulation provided by the 0.30 meters of air is way more than the insulation provided by that. So it's almost like you don't have the glass in there as far as stopping heat flow, except without that, you wouldn't have dead airspace. And again, this is fudging a bit because you'd have convection currents inside there that would kind of monkey that. But we can figure out what the heat flow is now, finally. So divided by and it's not much, 2.8 watts. So that's a really small heat flow through a window like that. Now, again, it's kind of a fictional window, but you could maybe do something if you could get really cheap single pane windows. Instead of having 2 of them, you could have 3 of them, and you could get reasonably good insulation that way. I've also seen plans to do things like at night or when it's cold outside, you could have some blow-in styrofoam insulation and then suck it out again during the day. But this is getting pretty fanciful anyway. Still, that's kind of a interesting little problem there. Okay, let's do one that throws something new into the mix and see how this one works. Here's the first one I wanted to do. We have a pot with a steel bottom that's 8.50 millimeters thick, that's a pretty thick steel bottom, actually. Actually, it's not completely unheard of. That would be about that thick. It's more likely to have an aluminum sandwich in there, but we're going to keep this simpler. So it rests on a hot stove, and area of the bottom of the pot is 0.150 meters squared, and the water inside the pot is at 100 degrees Celsius. I decided to change this. That's only 1 sig fig. I decided to change it to 97.6 degrees Celsius, which is the boiling temperature of water at 2,300 feet of elevation, which is the elevation of my house approximately. It's actually more like 2,340, but anyway, 97.6 degrees Celsius is the temperature of that, and 0.390 kilograms of water are evaporated every 3.00 minutes, which would be 180 seconds to 3 significant figures. So find the temperature of the lower surface of the pot, which is in contact with the stove. Huh. Okay, well, the thing is, we must have a certain heat flow into this pot because okay, and I didn't draw a very good bottom on this thing, but we want to know the temperature at the bottom, T sub B. The temperature at the top of this thing is T sub, we'll call it T sub C. It's going to be T sub cool, but it's going to be 97.6 degrees Celsius. And we'll have a certain amount of heat flow through the bottom of the pot and into this water, where convection currents are going to take over and keep the entire batch of water at the same temperature. But the heat flow through the bottom of this must be enough to evaporate that much water every 3.00 minutes. So we can calculate what the heat flow has to be. H, which is dq dt, or in this case, it'll be delta Q over delta T, is going to have to be enough to evaporate that much water. Well, let's see, the delta Q in this case is going to be M times the heat of vaporization of water. Okay? And the M is 0.390 kilograms. And the heat of vaporization of water somewhere. Oh, I tracked down that table that had those things in it. Excuse me, which is just something I photocopied out of the book. But down for the delta T, I'm going to have the 3 minutes there. So let's go ahead and stick this in and see what that heat flow has to be. 0.390 kilograms. And L sub V, let's see, I have to look that up because I don't have it memorized. Heats of vaporization for water. And you won't be able to read this, but it's just photocopied out of your book. It's 2,256 times 10 to the third, or 2.256 times 10 to the sixth joules per kilogram. So joules per kilogram. Okay, and that's the amount of heat that has to be going into this thing every 1.80 times. Excuse me, I got a tickle in my throat here. 10 squared seconds. And the kilograms will divide out, and I'll have joules per second, which are watts. So the heat flow here has to be let's see, 4.89 times 10 to the third watts. So this is maybe isn't completely unheard of. I know, or maybe it is a lot. I don't know, but it's just the problem I made up. So actually, if I was to do this again, I'd probably drop this amount of water being evaporated by about a factor of 10. So maybe 0.039 kilograms, because that's kind of high. But still, where's that going to come from? Well, it's the heat that's flowing through the bottom of the pan. So I'll have to have the thermal conductivity of steel times the area of the bottom of the pan, which we figured out here somewhere, I think. Or maybe we're given it, 0.150 meters squared, times the TH minus T cold, that's the bottom minus the top, and that'll be the temperature of the bottom is what we're trying to find. The cool temperature is actually the 97.6 degrees Celsius. The bottom is going to have to be hotter than that in order to transfer that much heat through. And this may end up being unreal. I can't remember if I made this problem up or if I got it from somewhere. And then I divided by the thickness of the steel, which is 8.50 times 10 to the minus third meters. All right, let's go ahead and plug in all the numbers that we have here. Oh, and we know the heat flow, it's that much. So let's see. Yeah, I'm going to start multiplying these things out. I'll solve for TB minus TC first. 4.89 times 10 to the third watts times the 8.50 times 10 to the minus third meters divided by the thermal conductivity of steel is 50.2 watts per meter Kelvin. So And by the way, for our test on thermodynamics, you'd be given this table or something like it. And then the area, I also have that in there. So nope, I forgot. There it is, 0.150 meters squared. I was thinking a step ahead, and I shouldn't do that. I should do one step at a time. So that'll equal T bottom minus TC. And just plug in the numbers and see what we get here. Let's see, for this, I'd end up with about, that's about 5, that's about 8.5. So around 50 for this, divided by 50 for that. So about, I'm guessing around 6, but I'm not sure. I get 5.5 for the temperature difference. So is there any place? I've got 3 sig figs, so 5.52. And it would come out Kelvin. Back here, I would have, this is meters squared, I'd have watt meters per Kelvin. I've got watt meters on top, so the watt meters divide out and I'll end up with Kelvin for the temperature. And that's TB minus TC, and that means that TB will equal, by the way, this could, it's a temperature difference, so it can be expressed in degrees Celsius as well. So that will equal TZ plus 5.52 degrees Celsius, and the cool temperature was 97.6 degrees Celsius plus 5.52, and we're going to lose a sig fig on that when I add it together. So I'll get about 102, I don't know, I don't feel like doing that in my head. Lazy. Actually, 103.1 degrees Celsius, which isn't so unbelievable after all. This is a problem you could do if it was sitting on a regular electric stove, but our new stove is an induction stove, so doesn't quite work that way. The temperature gets added to the steel in a different way. Anyway, there's one that involved time, and not in too hard a way. We were able to figure out the heat flow rate without having to do anything too extraordinary. But the next problem, we do have to do something kind of extraordinary. So get to use some calculus. Let's see, when the air temperature is below 0 degrees Celsius, the water at the surface of a lake freezes to form an ice sheet. And why doesn't freezing occur throughout the entire volume of the lake? Well, you've got a bunch of water there, and water will have convection currents, but there's something unique to water, and that is that water density is greatest at about 39 degrees Fahrenheit. And I don't remember exactly what that is Celsius. It's around 5 degrees Celsius. But that's something unique about water, that as you cool water down, like say a lake in the fall, as the temperatures are getting colder and colder, at some point, the water at the top will reach the density. Usually things are more dense as you lower the temperature. So if the average temperature of the lake is, say, 45 degrees, and you drop it down to 44 degrees, it's that the 44 degrees will be more dense than the 45 degrees. And so you'll get this stratification in a lake until you get some of the water being 39 degrees, and that's the most dense water ever gets. And so that will sink to the bottom of the lake, and that'll be the temperature of the water at the bottom of the lake. And then it'll get colder on top, but that colder water on top won't sink. It'll just do that. And so when you've got a lake, what you end up with is that, if this is our lake, the water at the bottom is 39 degrees Fahrenheit, and eventually the water at the top will be 32 degrees Fahrenheit. But as you go up here in temperature, from 32 degrees down to 39 degrees, the water becomes more dense. And so you get this stratification that's kind of a reverse of the usual, of what you would expect. But you'll have, there'll be a layer down above that where it's 38 degrees Fahrenheit, and then you keep going up there. But lakes freeze from the top on down is the trick on here. And first thing we're supposed to do is show that the thickness of the ice sheet formed on the surface of a lake is proportional to the square root of the time if the heat of fusion of water freezing on the underside of the ice sheet is conducted through the sheet. So what we'll imagine, let's see, if I can use this. You're going to need some numbers on the back of it. But we'll just imagine that our pond has a nice constant depth. So it'll make it a rectangular lake or something like that. But we'll imagine, for starters, that we have a really thin layer of ice up here at the top. And I'm just going to let the thickness of this layer of ice be dx. Okay, so I'm going to have x going in the up and down direction. So how much heat would it take to, and the lake has some area of A, which we're actually going to get to divide out of here, but how much heat would have to be extracted from the next little thickness of water dx that's got an area of A in order to freeze it? Well, for this, we're going to want to know the heat of fusion of water. That will be L sub F for water. And that's on the back of this sheet somewhere. Water. Okay, normal melting point, 273.15 degrees, which is 0.00 degrees Celsius. And heat of fusion is 334 times 10 to the third joules per kilogram, or 3.34 times 10 to the fifth. So we're going to use that number. Joules per kilogram. And remember, the water at the top of this thing is at 32 or 0.00 degrees Celsius. So we're at that temperature. And to freeze it, we just have to extract some heat from it without changing its temperature. And so what will we have to worry about? Well, this is per kilogram. So we need to think about, if we're, let's see, whoops, tried to combine two words. So to freeze a volume of A dx, okay, we need how much heat? heat removed. Well, let's see. AdX is the volume. I'm going to have to know the density of water, right? If I multiply this volume times the density of water, which is mass per unit volume, then I'd get the mass of that water. So the dm, the incremental mass, that I freeze will equal AdX, the incremental volume, times the density of water. And for density of water, we use a Greek letter rho. Density of water is about 1.00 times 10 to the third. I don't think it's on here probably, but it's a gram per cubic centimeter, but it's more like 1.00 times 10 to the third kilograms per cubic meter. Okay, so there's our incremental mass, and the heat we're going to have to remove, L sub F dm, in order to freeze that, is just going to equal L sub F times A times rho times dx. And so that's what we have to do. Okay, now what's that got to do with heat flow? Well, somehow we can set up a heat flow equation where presumably we'll be given the temperature up here. In fact, on this problem, we are given that temperature up there. The upper surface of the ice sheet is at minus 10 degrees Celsius. The underside is going to be at whatever that is. Actually, I'm going to pause for a minute and look up the temperature at which ice is, or water is, most dense. I've been finding a lot of these things on this website called the Engineer's Toolbox. And let's see. Density of water versus temperature. And it's back there in the engineering toolbox again. Except it doesn't give me the temperature very well, because it doesn't have it split up very well. Oh, great. That one's got it in, oh, degrees Fahrenheit. Okay, found a table. That'll be more helpful. Looks like it's at just about 4 degrees Celsius. So that's what we'll use for the bottom of our layer. And that's as good as I can get. So we may be down to, I don't know what would be down here. Minus 10 degrees Celsius. So this is the temperature cold and this is the temperature hot. So that's the direction of our heat flow. So let's see with our, what we've got here, what kind of an expression we could set up for this thing. The heat flow, which is going to be dq dt, is going to equal, well, the dq, this is the volume needed to freeze a little incremental thing, or the heat needed to freeze a little amount there. So I could write this as L sub F A rho dx over some time interval. And who knows what that's going to look like, but this will equal the thermal conductivity of ice this time. So I'll write that as K sub I times, it always gets multiplied by the area, which is the, in this case, the area of the lake. And what else goes up here? The T hot, in this case, not very hot, minus the T cold. And I divide by the thickness of the ice, which I'm going to let that equal X. Okay. But I'm going to start this with letting X equal 0. Now, I've got things like a dx over here, and I've got a's on both sides of this equation, so that'll divide out. So I didn't need to know that. But what does this equation turn into then? This is well, I don't know. It's just an equation. So I can set this thing up, and if I cross multiply on this thing, on the left side, I would get heat of fusion. Remember, I'm going to let the areas, well, I'll leave it in for one more step. A rho x dx is going to equal K sub I A times TH minus TC and dt on the tail end of this one. Okay, well, keep going with this thing. In fact, I'm gonna start it working on this sheet over here. Take the expression that I just got there and divide the a's out. So on the left side, I'll have the heat of fusion for water times the density of water times x dx is going to equal K sub I. I divided out the a's. I'll have T sub H minus T sub C times dt. Okay. I'm going to integrate both sides of this thing. Now, this is a constant, this is a constant, this is a constant, that's a constant, that's a constant. The only variables I have are x dx, or x, and t. So I can integrate this side with respect to x and this side with respect to t. And they're going to be easy integrals because almost everything that makes these things look scary are things that we know, just these constants. In fact, if I divide both sides by this stuff, I'll have the heat of fusion times the density of the water divided by thermal conductivity of ice, and then TH minus TC. And then I have x dx left on this side, and on the right side, all I have is dt. I know how to do these integrals, and it's been 40 some years since I took calculus. Although I did teach it once, so that probably doesn't count. But let's imagine we're going to integrate from no ice thickness to some final ice thickness. And we're going to integrate from time 0 to time t. And just see what we get. Well, the left side, if you integrate x dx, you get 1/2 x squared. So that'll turn into, I've got all my constants here bundled up together. K sub I times TH minus TC. Those are all my constants, and I'll have x squared over 2, and I'm going to evaluate it from 0 to x final. Well, that just gives me x final squared over 2. And on the right side, I'm integrating dt from 0 to t, I'm just going to get t there. Maybe I'm skipping a step of calculus. I'd get t evaluated at t and 0, which is t. Now, what's it say? Show that the thickness of the ice sheet formed on the surface of a lake is proportional to the square root of the time if the heat of fusion of water freezing. Oh, so I'm supposed to solve for the thickness of the ice. Okay, well, I think you can see I'd have these constants ending up over on that side as well as the 2 ending up on that side. So I'd end up with x final squared, not ending up, but it'll equal all this junk, which I'm going to rewrite as 2k sub I times th minus tc over heat of fusion times the density. All kinds of stuff got brought into here times t. All right. And then the thickness of the ice is proportional to the square root of the time. Well, yeah, x final squared equals that. But if you go for x final, you would get the square root of the time. So that's the idea. And then it says, assuming that the upper surface of the ice sheet is at minus 10 degrees Celsius and the bottom surface is at 0 degrees Celsius. Oh, that's right. I made a mistake here somewhere. Yeah, 32 degrees Fahrenheit is 0 degrees Celsius. I don't know why I bothered to look that up. That was a waste of time. Anyway, how long will it take to form an ice sheet 25 centimeters thick? Oh, okay, that'd be kind of neat. So let's see what happens if we plug in our numbers here. Now we're going to be just using this equation here. So the time needed will equal, let's see, heat of fusion of ice is, I wrote that down somewhere. Oh, it's on this sheet. 3.34 times 10 to the 5th. And that is joules per kilogram. The density of water in there, 1.00 times 10 to the 3rd kilograms per meter cubed. And so I should keep track of what kind of units I have over here. Oh, K sub I, the thermal conductivity of ice, which is 2.18 watts per meter Kelvin. So and I may have to, a watt is a joule per second, and that's probably, yeah, I'm going to write that as a joule per second and just put a second on the bottom here. Okay, and what else? Oh, now I forgot what the number was. K sub I, it was 2.18. So we've got that, and we have the temperature difference, which in this case is 10 degrees Celsius, 0 to minus 10, or 10 Kelvin. So, and we don't have a lot of sig figs on this. So that's the way it goes. And then I'm going to have to be really careful keeping track of my units here. Although I can see kilograms divide out here. I'll have joules per meters cubed there. I've got joules per meter down there. The joules will divide out, and I'll have meters or something per meter squared here. Oh man. Let's see, watts per meter Kelvin. Oh, that's a capital K. Okay, so the kelvins divide out. All right, I have to do this separately to try and make sense of this. Joules per kilogram times kilograms per meter cubed. On the bottom, joules per meter Kelvin seconds times Kelvin, and the kelvins will divide out, the kilograms will divide out, and I'll have joules per meter cubed on top and joules per meter second on the bottom. When I invert and multiply, I'll end up with meters, seconds, the joules will go away, over meters cubed, which is seconds per meter squared. All right, and that's all those constant things. But then I've got x final squared, which is 25 centimeters. That's 0.25 meters. And I'm going to square that. And that's divided by 2. Okay, so these meters squared will take care of those, and I'll end up with a time in seconds. Whew. All right. Sometimes the dimensional analysis can make you drive you just about batty. But let's plug in numbers here and see what we get. So 3.34 times 10 to the 5th times 1,000 times 0.25 squared. I hit a wrong key there. 0.25, square that. Divided by, and I'm going to get the 2 first. I think that's everything, I hope. And I get about, well, it's going to take a while. 4.8, and I even keep 2 significant figures. Yeah, it's pushing it a little bit. Let's just call it 5 times 10 to the 5th seconds. Well, how long is that? If I divide it by 3,600 seconds, which is how many there are in a, or multiply it times 1 hour over 3,600 seconds, I'd get, it's about 133 hours, which is, I don't know, how many days? 5.5 days. So it'd take in the neighborhood of 6 days to get an ice sheet 25 centimeters thick, if that's the case. And well, that's not bad, because you get the ice this thick and you'd be able to ice skate on that. You could probably almost drive your car on something this thick. So that'd be good. Okay, and then here it asks, if the lake is uniformly 40 meters deep, how long would it take to freeze all the water in the lake? Is that likely to occur? I think I can just revisit my previous calculation and replace 0.25 with 40. And yeah, I can do that. And I get a longer time. I'd get about 1.2 times 10 to the 10th seconds. And if I multiply that by 1 year over, let's see, it's about approximately 3.16 times 10 to the 7th seconds. And I don't remember exactly if that's right or not, but we've only got one significant figure. So divided by, yeah, it'd take about 400 years. Not likely to occur. We haven't had any winters that last that long, and they seem to be fading out. Okay, there's one more just kind of goofy problem, but see if you could set it up and see if you can go through it exactly like I did as far as setting it up and everything. But it's toward the end of the 21st century. That's the one we're in right now, I think. NASA has a thriving space colony on Mars. I got the idea to make this problem up after watching The Martian, and I'd read the book a couple times too. But after watching that movie, and then there was another Mars colonization book that my wife and I listened to while we were driving on road trips last year. But anyway, there's a swimming pool in a nicely heated building and a college with an engineering physics class. One night, as an experiment, the students from the physics class turn off the heat in the pool building, and the next morning, the pool supervisor walks into the room and sees that there's a very thin layer of ice, less than a millimeter, essentially zero, just beginning to form on the surface of the pool, and the temperature in the building is minus 40.0 degrees Celsius. He also discovers that whoever turned off the heat has damaged the heating equipment, which he will not be able to repair until the next supply ship comes in about 17 months. When word gets out that it was the physics students, they are not very popular, even if it is a cool experiment. If the temperature in the building stays at minus 40.0 degrees Celsius for the next 17 months, how long will it take to freeze the pool solid? And assume the depth of the pool is a constant 2.50 meters. So that's one. See if you can solve that one. It would be solved exactly like we just froze the lake. And so see if you can redo that calculation. And there's a homework problem very similar to this. So you can check that out. But I do this one for practice first. And so I will stop recording there.